we have tried to get the main aspects of wire harness design and automate them and put them in a Synera workflow. And I can quickly share this for you. All right. So what we see here is a back hatch of some generic car. It's not very important which one, but this is basically just the design space and the search space. And search space, I mean, for the searching of the optimal paths for all the cables. But let's start in the beginning. So we start out with a very basic data import that consists of data coming from basically an Excel file, just where we map which point has to be connected to which other point. So that's the electrologic. And that's the first step. That's the foundation for this algorithm to work. So we need to know which component do we have to connect with another component. Then we also do some pre-processing of the design space, because obviously in the first step it's not a voxel space, but just a regular geometry. So we need to process that as well. Then we do some processing of the data. That's probably not really interesting. And now from here we actually start doing the interesting stuff. So what we do is we actually don't use the whole search space here. So the gray area, that's the whole search space, but we don't use every part of that, but we use a reduced set of a search space that makes more sense in our case, and that is we reduce the search space to only the edge of all of the space. So we don't look inside, like in the middle of the volume, but we only look at the edge. And the foundation for the algorithm then is a line network that spans across all the interesting space that we deem interesting for cable routing and for cables to go there. And from this, on this network, we then look at the electrologic that we imported before in data, and then apply our algorithms that search the optimal path in this network. And the result you already saw before is this. And so maybe you will ask what is the optimization criteria here? And for us at the moment, it is, we can also have a bit of a nicer representation of the cables. And the optimization goal here is, for one thing, find the shortest possible cable length, because we obviously don't want to waste any cable. And on the other hand, it's also the bundling of the cables, because many cables go into the same direction. But if we only look for the shortest path, they will go anywhere. Like one cable will go down there, one other cable will go up there. But we don't want this in reality. So we want to reflect the constraint that we want to, if two cables go in the same direction for an extended amount of, for an extended distance, we want to have them in the same bundle. And that's the second big optimization criteria here. And that's what our algorithms do. So with a genetic algorithm, we search for the optimal branch points, and that is where do all the cables go through. That's like very central points in the cable harness. And then in the second step, we apply heuristics and search algorithms to find the optimal path using the points we have found before. And then the result is what you see here, which is not complete, to be honest. So there's a lot more to implement, but this is our this is our first step in these directions to actually apply AI algorithms to generate an optimal wiring harness.
Super interesting. So how would this change the work of one of these 25 harnessing engineers at an OEM at one plant that Roland talked about?
Well, in the best case, it would basically replace them and automate. Well, it's a kind of a difficult road we're going here, right? But in the end, we want to make their work easier and reduce communications between different departments. I think that's a really great that's a really important point there. And by reducing the amount of communication, we are gaining development time. So we're saving time. And what would be a concrete change for the people working on these wiring harnesses is that they would, for once, they would get well, an optimal harness and not only one working solution, as Roland said before. So the quality of the results will improve. And we have the possibility to, by all these time savings and by automating the process, we can generate a lot more variants and apply these to so many different problems and different geometries, which makes it really flexible and reduces the amount of manual work, essentially. So it's more like the people would have more like a managing role and less of a actually labor role, you know.
And one minor addition to this, the interesting thing is that you don't need to get rid of the people that save time here, but they can do the real engineering work. So as we know, as with our history of engineering services we provide, there is a lot of process fulfillment we need to do, a lot of tasks we need to fulfill around real engineering, around real creative work. And having the automation here, we get the opportunity to spend the time of the engineers with all their knowledge, with all their intuition. We can spend this time wisely. There are a lot of problems still to solve. We don't say that this workflow will solve all the problems that you could encounter, but it allows certain types of work to be done automatically. And this allows the engineer at the other side to really concentrate on the problems that are still there.
One problem you could encounter is that there is no solution that an automation could find. What do you do then?
Yeah, so this is a question that we heard several times meanwhile, and of course this is the main thing, the main issue. What do you do if there is no optimal solution, especially in the early stage? There are not all the way through the sheet metal. There aren't any holes, for example, that are there especially for the wiring harness, and of course then we can't find a solution. And you could tackle this in 2 steps, more or less. What you can easily do is just make a hole in there. The workflow can reload the input data. So the easiest way is that you go to the colleague who always said where this hole should be for the wiring harness. You can just add one. You can add another one in the input data. And as Daniel is showing live here, the geometry is there, and you can reload it, and there is a new hole. And if you couldn't find the way in the first step, with the knowledge of the colleague that is available, you just put it in the right place. You can still use the optimization, as mentioned before, additional with the manual work of adding holes, so no problem there. Another step that is already available more or less in Synera is using AI optimization, if you want. So you need to define all the places where a hole could be, and Synera workflow could be able to use the ant colony optimization algorithm that is already available in Synera to go through all the possible position of holes and find the best one. Another optimization approach, which is not yet implemented, so that would not be ready, but it is available, and we could just do that.